In the previous video, we derived the Taylor series for a complex function in a region of analyticity. And in this second video, we're now going to look at expanding complex functions in regions where the function is not analytic. For example, it might not be differentiable in some part of the region. Specifically, we're going to be looking at rings or annuli of analyticity, where there's a smallest and a largest radius where the function is analytic. You remember in the previous topic, we derived the deformation property in multiply connected regions by identifying a simply connected subregion using a channel. Here we're going to similarly define a simply connected subregion within that annulus of analyticity, and we'll then apply Cauchy's integral formula to derive Laurent series. As a quick recap of the previous video, we looked at the generalized Cauchy integral formula, and we got that by differentiating the original Cauchy integral formula under the integral sign. This allowed us to relate the value of a function and of all of its derivatives to the values of that function along a contour enclosing the point of interest. We also derived the Taylor series for a complex function in a circular region of analyticity. And we did this by identifying coefficients in a power series expansion as the function's derivatives. We then looked at 1 over z as an example. These are the intended learning outcomes for this video. So after watching this video, you should be able to understand the expansion of a complex function in an annulus of analyticity as a Laurent series. And you should also be able to interpret a Laurent series as a sum of two complex power series, each with a different region of convergence. There's going to be a power series with positive powers that converges inside a circle, and then there's going to be another complex power series in negative powers that converges outside a circle. Taken together, the region of overlap for these two power series defines an annulus. Right, let's get going.
In this video, we're going to talk about Laurent series. In the previous part, we saw how for some complex function f that is analytic on and within a circular contour, the Cauchy integral formula can be used to give us the Taylor expansion. But what can we say about the expansion of functions in regions that contain singularities? We'll see that we will be able to expand the function in something called a Laurent series. So to begin, what can we say for a function in regions that contain singularities? In other words, they are no longer what we refer to as simply connected. Well, consider the following. Let's imagine some complex function with the following region of analyticity. I'm going to need some circles. That's one. And I'm going to shade in this central circle. And shade outside this other circle. Okay, so this is some region in the complex plane, and any region that is shaded is a region where our function of interest is not analytic. So grey means a region of non-analyticity. I'm going to label a couple of important points, so I'm going to say that these circles are centered at the point z0. I'm going to give the radius of this inner circle as r, and the radius of this outer circle as capital R. I'll write this down, that little r is the minimum radius of analyticity, and capital R is the maximum radius of analyticity. Our function is only analytic in the white region, the white ring. I'll note also that we can take the minimum radius of analyticity. We could assume that that tends to 0 if we're considering a singularity that is a point. And we could consider the maximum radius of analyticity tending to infinity if there are no more singularities outside the small radius r. Suppose we have a function f of z that is analytic in the annular region, so the annulus or ring, bounded by circles of radius little r and big R. But our function f of z is not analytic in that central grey region within the circle of radius r centered at z0. Okay, well, it turns out that if we have this setup, then the Taylor expansion that we encountered in the previous video, the derivation of a Taylor series, does not apply. We can no longer expand our function as a Taylor series. So, for example, if there's a singularity at the point z0, that means that we can't use our previous assumption that f is analytic on and within the circular contour. How do we approach this? Well, I'm going to take a copy of this picture. I've made a copy of what we had above, and I made things a bit simpler by removing the labels for the radii of those different circles. Okay, so how should we proceed now? Well, let's now add two circular contours that lie within the region of analyticity. I'll make these different colours. The first one which we're going to call C1 is this blue contour, and the second is this green contour, C2. I'm going to label their radii. The green one has radius R2, and the blue one, C1, has radius R1. I'll note on the side here that we have the hierarchy that the radius of the small grey region, R, is less than the radius of the circle C2, which is less than the radius of the circle C1, and that has to lie within the largest radius of the region of analyticity, capital R. I'll note here, for some point w, first of all let's consider w lying on the circular contour C1. We've let the distance w minus z0 equal this radius r1. Similarly, for a point w resting on the contour C2, we have that w minus z0 is this second radius r2. I'm noting these because it'll be important in manipulations that we do later. I'm now going to state a result that we're going to spend the rest of the video proving. Consider a point Z lying between the circles C1 and C2. I'll draw an example point in the diagram. Z might be over here. We will show that there is a generalization of a Taylor series called a Laurent series. So a Laurent series, and it is given by this expression. Our function value f, which has this region of analyticity that we have in the picture above, the function value at a point z lying between the circles C1 and C2 is given by the sum from n equals 0 to infinity of coefficients times z minus z0 to the n plus the sum from n equals 1 to infinity. Note that they start at different values, these two series. This second one is a sum of terms qn, lots of z minus z0 to the minus n. I'll note here we have ascending powers of z minus z0, and here we have descending powers of z minus z0. This is a really important result called a Laurent series. Laurent series. And we're going to spend the rest of the video deriving this. I'll note here that the coefficients Pn are given by 1 over 2 pi I, the integral along the circular contour C1 in the picture above, that's the blue circle, of f of w over w minus z0 to the n plus 1 dw. This is where w is constrained to lie on the blue circle C1. These other coefficients qn are given by 1 over 2 pi I, the integral, now around the green contour C2 of f of w over w minus z0 to the minus n plus 1, where now the integration variable w lies on the green circle. These expansion coefficients are something that we're going to derive later. So we're now going to derive this result using Cauchy's integral formula. So, proof. I'm going to take a copy of our picture above. And as before, I'm going to remove some of these labels for clarity. Okay, so we've got our copy from above. Now notice that this setup looks very similar to what we had in topic 5 when we were looking at multiply connected regions. We notice that the circles C1 and C2 form the boundary of a multiply connected region. And this multiply connected region, the region between C1 and C2, is a region on which f of z is analytic. We're now going to be able to play the trick that we used in topic 5 when dealing with multiply connected regions. We're going to use a channel to convert this multiply connected region into a simply connected region. I'll write that down. We may add a channel to convert this to a simply connected region. As before, I'm going to make a little gap in these contours C1 and C2. And we can add this bit and this bit to define a narrow channel. I'll call the red bit CA and the purple bit CB. And you can see now we've defined a closed contour lying entirely in the unshaded analytic region. I'm going to add the orientation of different segments. We're going to have C1 traversed in the anticlockwise sense. CA is then going to be traversed in the ingoing sense. Now C2, this green circle, is now going to be traversed in the clockwise sense, so opposite to C1. Finally, to keep things consistent, CB is going to be oriented outgoing like that. You might anticipate that, as before, we are indeed going to take the limit of 0 channel width. First of all, I'm going to write the new simply connected closed contour. Let's call it B. Consists of those different paths C1, CA, C2, and CB. Because it's simply connected, we can use Cauchy's integral formula to express the function value within that region bounded by the new contour B. Cauchy's integral formula gives us that the function value at some point z is given by 1 over 2 pi I, and we're now taking the integral around the simply connected closed contour B of f of w over w minus z dw. This is our Cauchy integral formula as normal. We know that we can write this out as 1 over 2 pi I, and then the sum of the contributions along the different paths making up the closed contour B. So this would be the integral along C1 plus the integral along CA plus the integral along C2 plus the integral along CB. As I said earlier, we can take the narrow channel limit, where now the contribution along CA will be equal but of opposite sign to the contribution of the integral along CB. Therefore, the channel contributions cancel, and as before, we can consider the ends of the paths C1 tending towards each other, the ends of the path C2 tending towards each other, and so our contours C1 and C2 again become closed. I'll write that here. We take the narrow channel limit. That means that the contribution along CA and the contribution along CB cancel. We're therefore left with 1 over 2 pi I, the integral along the closed contour C1 of our integrand f of w over w minus z dw. Now, in the picture above, the contour C2 is traversed in the clockwise sense. By convention, we want to write closed contour integrals in the anti-clockwise sense. And we can ensure that by adding a minus sign and assuming that the contour C2 is indeed traversed in the conventional anti-clockwise sense. So that means that down here, we're going to get a minus sign in front of our closed integral around the contour C2, where now both these integrals are traversed in the anti-clockwise sense, and the minus sign is accounting for the fact that we have flipped the orientation of the C2 traversal. And we have the integrand f of w over w minus z dw. I'll note here the sign is from original clockwise traversal. Right, I'm going to define these two terms as f1 of z plus f2 of z, where f2 contains the minus sign. And we're now going to investigate both of these contributions to our function f of z separately. First of all, let's look at f1 of z. Well, for f1 of z, the integral is around the contour C1, so w lies on C1, and that means that the absolute value of w minus z naught, which is the radius r1, that is greater than the distance between some point z in the region between C1 and C2 from the centre of those circles z0. We're now going to perform very similar manipulations to those we did looking at Taylor series in the previous video. As for Taylor series, earlier, we're going to expand the 1 over w minus z term in the integrand. And the way we do that is we're going to add and subtract the same term in the denominator. We're going to have w minus z naught minus z minus z naught in the denominator. We can take out our factor of w minus z naught to leave us with 1 over 1 minus z minus z naught over w minus z naught. This is precisely the convergent geometric series that we spotted in the previous video. And this is convergent because we have that the absolute value of z minus z naught over w minus z naught is less than 1. Substituting this expansion of 1 over w minus z into our expression at the top of the page for f1 of z gives us, as earlier, this gives us that f1 of z is the sum from n equals 0 to infinity, and we can write it as a power series in z minus z naught, where the coefficients Pn And you can check this for yourself. It's the same manipulation as in the previous video. These coefficients are given by the integral around C1 of f of w over w minus z naught to the n plus 1 dw. This term is the usual Taylor series that converges for all z inside that circular contour C1. Thus, by construction, this function f1 of z is analytic inside our blue contour, the large circle C1. Let's now look at the other term that we're interested in, f2 of z, which is the second term at the top of the page. Now let's look at f2 of z, which is given by 1 over 2 pi I, the integral along C2, and I'm going to take the minus sign inside the integrand. We have minus f of w over w minus z dw, and that minus sign comes from the orientation of our circular contour. This is an integral along C2, which is the inner green circle. That means that w, the integration variable, lies on C2, which also means that this inequality holds. The distance between a point z, constrained between the circles C1 and C2, the distance from that point to the center of the circle is always going to be greater than the radius of the circle C2. So you might be able to guess that again we're going to be looking for a convergent power series, but it's going to look slightly different to the one that we found for f1 of z. Okay, returning to our expression f2 of z, we have this minus sign that we're going to move to the denominator. So we have the integral around c2 of f of w over, now it's z minus w dw. Looking at that denominator, we're going to expand 1 over z minus w, again by adding and subtracting the same term. We're going to have z minus z naught minus w minus z naught. Now we're going to take out a factor of z minus z naught in the denominator, and that will leave us with 1 minus w minus z naught over z minus z naught. And you'll see that this is very similar to what we had for f1 of z above. We can spot that this is going to be a convergent geometric series. As long as the absolute value of w minus z naught over z minus z naught is less than 1. I'll therefore write that this is a convergent geometric series outside the circle C2. Right, substituting this into our expression, we have f2 of z is 1 over 2 pi I, the integral around the contour C2. We have our 1 over z minus z naught factor and this multiplies f of w over, and then we have 1, this term here. We're now going to substitute in our convergent geometric series, and we can take out the factor 1 over z minus z naught because there's no w dependence. We now have the integral of f of w, and we then multiply by our convergent geometric series of w minus z naught over z minus z naught to the power n dw. Here the integral of the sum is the sum of the integrals, and we can tidy this up to get 1 over 2 pi I, the sum from n equals 0 to infinity of 1 over z minus z naught to the n plus 1, the integral along C2 of f of w times w minus z naught to the n dw. The last step is going to be a shifting of the summation index. We're going to relabel n plus 1 as n. And with that we end up with the sum from n equals 1 to infinity of z minus z naught to the minus n times 1 over 2 pi I, the integral along C2 of f of w, and then w minus z naught to the n minus 1 dw. Therefore we have that f2 of z is the sum of coefficients qn times z minus z naught to the minus n, where the coefficients qn you can spot above are given by these expressions. And we're done. We can therefore write that our function, where z is in that annulus between C1 and C2, that's given by f1 of z plus f2 of z, which is the sum of terms in ascending powers of n plus this sum in terms of descending powers of n. Once again, we've arrived at our Laurent series. I'll note that these first terms, the ascending powers, are sometimes called the analytic part. And this series converges inside C1. This second part, in descending powers of z minus z naught, is sometimes called the principal part. And this converges outside C2. And taken together, these two parts both converge within that annular region. And so we have successfully found a power series in positive and negative powers of n with which to express our complex function, f of z. As a quick point here, if we went back to assuming that our function was analytic on and within that larger circle C1, then the coefficients qn would vanish, and we would recover a Taylor series as before. A couple more things to note. Note that if f of z is analytic at every point on and within the large circle C1, except the point Z0 then we can take the radius of the smaller circle, C2, that can be taken arbitrarily small. With the result that the Laurent series you obtain is valid for z minus z0 lying between 0 and the radius of the larger circle, R1. There's another simplification we can make to our Laurent series, and that comes about by our assumption that the function is analytic in the annular region. If f of z is analytic in all the annular region, we could deform, recall our deformation property from the earlier video, we could deform the contour C1 into C2, or indeed vice versa. Or we could deform them to meet somewhere in the middle, somewhere in between. And that would not alter any of the analysis. This would not alter the coefficients Pn and Qn. That would mean that we could write our Laurent series instead as f of z is the sum from n equals minus infinity to infinity of some merged coefficients an z minus z0 to the n, where these coefficients an are given by 1 over 2 pi I around some closed contour C. This could be C1 or C2 or something in between of our normal integrand f of w over w minus z0 to the n plus 1 dw. Here we have that n is a natural number, so 0, plus minus 1, plus minus 2, etc. This here is another way of writing our Laurent series, where the coefficients an, and this is valid for z minus z0 lying between the small r, which is the smallest radius of analyticity, and big R, which is the largest radius of analyticity. As a final small point, to write out our function f of z in full, we would have something like a term a minus 2 over z minus z0 squared plus a minus 1 over z minus z0 plus a0 plus a1 z minus z0, and so on. Right, that's the end of this second video of topic 6. As a quick recap, we have managed to expand a function in a multiply connected region by identifying a simply connected region and using Cauchy's integral formula to find convergent series in an annulus of analyticity. And that gave us the Laurent series, and we've seen a couple of ways of expressing those. In the next video, we're going to go through some examples of how to find Laurent series. Thanks for listening.